Hi everybody, this is Professor Cary Troy. I'm going to talk to you today about the hydraulic jump. As you can see from the quote, few things in life are as beautiful and mysterious as the hydraulic jump. I think it was Winston Churchill that said that. I'm kidding. I said that. I say that about all the flows, but this one really is special. This is a laboratory setup of a hydraulic jump. So we have a head tank here. The water is dyed pink so you can see it more easily. This is called a sluice gate. So the water is forced out a very small opening down here, and it is supercritical, and then it jumps to be subcritical downstream. And you see all of this white water and turbulence, and that's really the hallmark of a hydraulic jump. So you can see all of the turbulence generated where the flow is jumping from supercritical to subcritical flow. And there's a lot of air entrained into the flow. You see a lot of bubbles associated with the turbulence near the free surface, and a pretty amazing phenomenon. Okay, so I just wanted to talk through a couple of the different scenarios where you actually get a hydraulic jump. How does it actually come about? The first one I'll talk about is what you just saw, the laboratory setup. In order to get a hydraulic jump, somehow you have to maintain supercritical flow upstream and subcritical flow downstream. And remember that supercritical flow is shallow and fast, and subcritical flow is deep and slow. And so in order for that to happen, one way you can do that is what we just saw. You have a sluice gate that is going to maintain a low flow depth, and if it's below the critical flow depth, that flow will be supercritical as it shoots out of the sluice gate. The flow in must equal the flow out. And then downstream, if you put a weir or some sort of an obstacle in place, the flow has to be deeper than the obstacle once a steady state is reached, and you'll have deep flow downstream. So essentially maintaining supercritical flow upstream and subcritical flow downstream. And this was what the hydraulic jump would look like. And what we're going to try to quantify later on is just how the flow is going to jump from one depth, y1, to a downstream depth of y2. Okay, so I just wanted to talk through a couple of the different scenarios where you actually get a hydraulic jump. How does it actually come about? The first one I'll talk about is what you just saw, the laboratory setup. In order to get a hydraulic jump, somehow you have to maintain supercritical flow upstream and subcritical flow downstream. And remember that supercritical flow is shallow and fast, and subcritical flow is deep and slow. And so in order for that to happen, one way you can do that is what we just saw. You have a sluice gate that is going to maintain a low flow depth, and if it's below the critical flow depth, that flow will be supercritical as it shoots out of the sluice gate. The flow in must equal the flow out. And then downstream, if you put a weir or some sort of an obstacle in place, the flow has to be deeper than the obstacle once a steady state is reached, and you'll have deep flow downstream. So essentially maintaining supercritical flow upstream and subcritical flow downstream. And this was what the hydraulic jump would look like. And what we're going to try to quantify later on is just how the flow is going to jump from one depth, y1, to a downstream depth of y2. So this is an example showing that situation where you would have the water shooting down a very steep slope. This is in St. Anthony Falls in Minnesota. And then you have a large hydraulic jump here, and engineers will actually design these spillways or these structures in order to dissipate a lot of the energy in the hydraulic jump. Another kind of example where you see hydraulic jumps in nature is if you're hiking or you see a stream or river and there's an obstacle in the river like a log or a rock. The flow will back up and rise up to go over the rock or the obstacle, and it can be supercritical going down the backside of the object, and then it will jump back up to be subcritical if the river is already subcritical. And you'll see these all the time when you're hiking. It might be an individual rock, or it might be something that's going across the entire stream. You see this white water on the downstream side of the object, and that's really kind of a miniature hydraulic jump.
Just do this, Julian.
So this is a small example of that, a little stick in a river and the baby jump downstream of it. Okay, now let's talk about how we quantify the hydraulic jump. So there's really two elements of the hydraulic jump that we're looking to quantify, and we're going to use the specific energy framework in case you can't recognize this diagram over here in the lower right-hand corner, to describe the hydraulic jump. So the first thing is the jump itself. So with y being the axis here and our critical depth here at the turnaround point of the specific energy curve, flow is going to go from the supercritical limb, which is the lower one, to the subcritical limb, okay? And so it's going to go from y1 to y2, so increasing in depth and going from super to subcritical, okay? The second thing that's going to happen is that you notice it didn't just jump straight up, it jumped up and over. And we're thinking about a flat bottom here, just so that you know. There's no shift to the left or the right due to the elevation change of the channel. In this case, all of that leftward shift from super to subcritical is related to the lost energy that the jump is dissipating in all of this turbulence here, okay? So in essence, we want to quantify two things. So these items are, number one, what is the downstream depth given the upstream depth? What depth will it jump to? And then the other one is, what is the head loss? So what is the leftward shift on the specific energy diagram? Okay, so how do we actually quantify the hydraulic jump? Well, it's pretty cool. So we have our overarching energy equation, and you might think, well, can you use the conservation of energy for this crazy flow? And the answer is yes, as long as we're accounting for the energy that we're losing in all of the turbulence here that we have in the jump. And so that's where the head loss is important and needs to be factored into this equation. So one thing to think about is that if we're looking for the head loss, if we knew the Y2, we could easily calculate the downstream specific energy, and if we knew Y1, we could do that as well. Typically, the problem is where we know Y1 and we're trying to figure out Y2. So if we can figure out Y2, we can solve for the head loss very easily. So let's focus on trying to get a formula for Y2. So conservation of energy, that would be this. That doesn't really help us. We still have two unknowns. We have Y2 and the head loss. The other equation we can throw at this, believe it or not, is the conservation of linear momentum. Okay, so forces is equal to the fluxes. Arr! And so what are the forces acting on this control volume if we consider the blue fluid here to be our control volume? Well, on the left-hand side, we have pressure. Okay, so pressure is from the fluid outside of the control volume acting back in on the control volume. That's one force, and it's assumed to be a hydrostatic pressure distribution, so you can relate the depth to the mean pressure there. And then the same is true for the downstream subcritical part of the control volume, where you have the pressure from the fluid downstream acting back in on the control volume, and that would be another hydrostatic pressure distribution to relate the depth to the pressure there. So those are the two forces. There's really no other forces going on. We're not considering friction from the bottom of the channel. That's really sort of a separate issue to the hydraulic jump. The jump will take place regardless of whether you have friction at the bottom or not. So to make it easy, we will say we have no friction at the bottom of the channel between 1 and 2. Those are the forces, and then for the fluxes, we just have a rho VQ going in and a rho VQ going out if we do one-dimensional kind of formulation. And so the conservation of linear momentum actually looks like this, right? So our fluxes, we have an inflow here, that would be the minus Q here, and an outflow at the right-hand side, that would be the plus Q. And if you write these pressures in terms of the depths and you rewrite the velocities in terms of the depths as well, you can derive the following formula. So this formula is for Y2, which is the key thing that we want. It gives it to us in terms of Y1, so that has to be known, and the upstream Froude number. So in order to calculate the upstream Froude number, obviously we need not only Y1, but we need to know the specific flow rate, which is typically given in these problems. But this is a really cool derivation here. I recommend those of you that are interested in trying to understand kind of where these formulas come from, try to go between this conservation of linear momentum equation and this one here, and that will give you some insight as to where that comes from. So what is that formula actually telling us about how hydraulic jumps jump and how they lose energy? This is a plot on the specific energy diagram for a certain flow rate, and what I'm plotting here is what that formula will predict for 3 different upstream Froude numbers, 2, 5, and 10. And what you see is that the highest upstream Froude numbers are associated with the most loss in energy. So remember, a leftward shift is all related to energy loss for the hydraulic jump. And it's also got a lot of elevation change in terms of the depths going from Y1 to Y2. as the upstream fluid number goes closer to 1, which is, if it was above 1, it wouldn't be possible to have a hydraulic jump because you can't jump if the flow is not already supercritical upstream. But a fluid number, let's say of 2, which is close to the critical of 1, it could still jump. It's supercritical, but you notice that the jump is much more modest. Not only is there only a small vertical gain, that's the jump from y1 to y2, but the head loss associated with the jump is actually tiny. That's the leftward shift between these two triangles. And so the key takeaway here is really that the higher the upstream fluid number, the more vigorous the jump is and the more energy will be dissipated. Okay, and that video that I showed you before with the red fluid in the laboratory, that was a very high upstream fluid number hydraulic jump. And that's the one you want to keep in your head when you're thinking about the case here for the black square. On the other end, a fluid number of about 2, that would be closer to that little jump that I showed you where the flow was going over the log in the stream. So when you have a low upstream fluid number, the character of the jump is more wave-like. Okay, it's not going to have a lot of this white water and not going to be nearly as energetic. All right, well that's a wrap basically. This is the summary here. Remember that a hydraulic jump, the flow is jumping from super to subcritical. When it jumps, it also jumps over to the left, and that is associated with all of the energy that you lose in the hydraulic jump. In order to quantify the vertical and horizontal shifts of the hydraulic jump, we have two different formulas. One is that the downstream depth is related to the upstream depth using this equation here. And the other one is our usual energy equation. Again, we're considering a flat bottom here, so there's no change in the bottom elevation between 1 and 2. If that's the case, then the change in specific energy is entirely due to the head loss. Once you know Y1, you can plug it in for E1, and once you know Y2, you can plug it in for E2, and you get the head loss directly that way. So I hope this video has been helpful, and I wish you luck with your hydraulic jumps.